In this lesson, we are going to solve this question I have here on the screen. The question says we should use Northon's theorem to find the current in the 10 ohms resistor connected between node A and B. So let's look at how you are going to solve this question. So to solve this question, the first thing I'll do is that I'll take out the 10 ohms resistor here and then calculate the short circuit current, which will be Northon's current. And after that, we'll solve for Northon's resistance, then we draw Northon's equivalent circuit, then calculate for the current in the 10 ohms resistor. So we're drawing this circuit. I have what I have here on the right side. Okay, so we don't have the 10 ohms resistor in the circuit anymore. Okay, so you've taken it out and then you're going to calculate for the short circuit current, which is what Northon's current. Okay, so to do this, okay, I'm going to transform this circuit here, okay, to a more simple way that it will be clear for us to use for calculations. So let's look at that. Okay, so with this circuit here that I have on the right hand side, okay, I have transformed into what you have here on the left hand side. Okay, so you see that it is the same circuit. Okay, so I have my Northon's current here. Okay, the direction is assumed. Okay, you choose the direction that you want. Okay, it's just that the signs of the answers will be different. Okay, depending on the direction that you choose. So you have Northon's current here. So now you see that this circuit here looks much more easy to deal with than what you have here on the right side. So I'm going to work with this circuit, or they are the same circuits. So let's go ahead. Okay, so all you need to do here is to calculate for what Northon's current IN. Okay, that's all we need to do here. Okay, so to do this, to calculate for what IN, okay, you'll have to know the total current flowing in this system here, okay, which I'm going to name as I. Okay, so to calculate for what Northon's current, okay, we will have to know what this total current was I. Okay, so let's calculate for this total current I. So to calculate for total current I, you will have to know the effective resistance of this circuit here. Okay, so you are going to go ahead and then calculate for the effective resistance, then we will use that to calculate for the total current in this circuit, since you know the voltage also. So you see that these 2 ohms resistor here and then this 6 ohms resistor are in a parallel connection, and also this 4 ohms is in a parallel connection to this 8 ohms. Okay, and at the end these 2 parallel resistors, okay, will be in series with what these 12 ohms that I have here. So that means what 2 and 6 will be in parallel and then they will become one resistor. They will give an equivalent resistance, and then the 4 and the 8 too will be in parallel and then they will give an equivalent resistance, and these 2 equivalent resistance will be in series with what the 12 ohms here. So we will have the total resistance to be equal to 2 parallel 6 plus 4 parallel 8 plus 12. So this will be the total resistance. So let's calculate for the total resistance. That was 2 times 6 divided by 2 plus 6 plus 4 times 8 divided by 4 plus 8 plus 12. Okay, so let's simplify this. So simplify this, I have 2 times 6 divided by 2 plus 6. That gives me 3 on 2. Okay, plus 4 times 8 divided by 4 plus 8. That gives me 8 on 3 plus 12. Okay, so I'm going to add the 3 on 2 and then the 8 on 3. So 3 on 2 plus 8 on 3. That gives me 25 on 6 plus this 12. Okay, so that gives me 25 plus 6 times 12, that will be 72. Okay, so this will be equal to what? 97 over what? 6. So that what the equivalent resistance. So you have what the total resistance in this circuit to be equal to what? 97 on 6 ohms. Okay, so now that you know the equivalent resistance, you can calculate for the total current in the circuit. So you know that voltage equals what? The product of current in the resistance. So you therefore have current to be equal to voltage over resistance. So that will be equal to what? 10 divided by the 97 on 6. So this will be equal to what? 10 times 6 on 97. Okay, so this will be equal to what? 60 on 97 amperes. So that's what the total current in this circuit here. So let's write this down. So you have what? I to be equal to 60 on 97 amperes. Okay, so now let's continue. Okay, so now that we know I, okay, I'm going to use this I here to calculate for the what? Current flowing through this branch here, okay, which is the short circuit current, known as what? Norton's current. To do this, okay, there are two ways here, and I'm going to teach you all these two methods that you can use to calculate for what? This current IN here. Okay, so first of all, you know that what? The current flowing from the power source is what? 60 or 97 amperes. Okay, so we can use this value to calculate for the current across these 2 ohms resistor. Okay, same way you can use it to calculate for the current across what? This 6 ohms resistor here. And then when you do this, you are going to use these two values to calculate for what? IN. So let's look at this. So I'm going to name this current as IB, and I'll name this as IE. Okay, and then I'll name this current as IC, and then I'll name this as ID. Okay, I don't think you are going to use this current ID here, but let's write it there. Okay, so now since you know the total current from the source, okay, we can use it to calculate for the current across the 2 ohms resistor, which is what? IA, by using what? Current division. So applying current division here, I'm going to see that IA will be equal to 60 on 97, okay, times the 6 ohms resistor, that's times 6, divided by the 6 ohms resistor plus what? The 2 ohms resistor. So that what? 6 plus 2, and that will give me what? 8. Okay, so let's calculate these values and see what you get for what? IA. So 60 on 97 times 6 on 8. So that will give me 45 on 97 amperes. On 97 amperes. Because that's the current IA here. Okay. And then we have another current here, IB. Okay, so calculating for IB also. I have IB to be equal to what? 60 on 97. Okay, the same current division rule that we are applying here, and that will be equal to what? 2 divided by 8, because you are finding the current in the 6 ohms resistor. So let's see the value of this also. Okay, so when I did this gave me 15 on 97. This gave me 15 on 97 amperes. Okay, you can still find this IB here, okay, by subtracting IA from what? The total current. Okay, you still get the same answer. So now I'm going to use the IA and IB values to find what? IC. Okay, so I'm going to use IA and then IB to find what? IC. Okay, so when you look at the circuit closely, okay, you see that what? This IA here is flowing to what? This part of the circuit. Okay, so you can consider IA to be a source current for this part of the circuit, and then IB also is also flowing to what, this part of the circuit. So you can consider IB also to be a source current for what, this part of what, it includes the 4 and the 8 ohms resistor. So the IB is also what, a source current for what, this part of the circuit. So you can use these two source current values to calculate for the what, current flowing through what, the 4 ohms resistor, which is what, IC. And then after getting IC, then you are going to calculate for what, Norton's current, what, IN. So now our main target here is to what, calculate for what, IC. Okay, so let's look at how you are going to do this. So this right side of this circuit here, okay, has what, two current sources. Okay, one which is IA, and then the other which is what, IB. So you're going to use IA and then find the current flowing through what, the 4 ohms resistor, which is what, IC. Then afterwards you use what, IB to find the current flowing through what, the 4 ohms resistor, and then the sum of these two current values will be the total current flowing what, the 4 ohms. So let's do this. So using IA as the current source, okay, using IA as the current source, we're going to have IC, which are named what, IC1, okay, to be equal to 45 divided by what, 97, because you're considering what, IA to be the what, source current. Okay, so that will be times 8 ohms, okay, divided by 4 plus 8, that will be what, 12. So let's find the value for this. So you have 45 divided by 97 times 8 on 12. This will give me 30 on 97 amperes. So when IA is acting as the source current for this part of the circuit here, the current that will be flowing through the 4 ohms resistor named as IC1 will be what, 30 on 97 amperes. Same way, when you have the IB to be the source current, we'll have 15 on 97 times 8 times 8 on 12. Okay, let's see the value of this also. So this will give me 10 on 97 amperes. Okay, so when IB is acting as a source current for the right side of this circuit here, okay, then the current flowing through the 4 ohms resistor, which is I2, will be what, 10 on what, 97 amperes. Okay, so at the end, we have to what, calculate for the total current flowing through what, the 4 ohms resistor, which is what, IC. So let's look at how you are going to do that. Okay, so now we have IC, which is the current flowing through the 4 ohms resistor, to be the sum of what, these two values, which is what, IC1 and then IC2. So you have what, IC to be equal to IC1 plus IC2. Okay, and this will be equal to 30 on 97 plus 10 on what, 97. Okay, and this will be equal to 40 on 97. Okay, 40 on 97 amperes. So that was the total current flowing through what, the 4 ohms resistor. Okay, so now that you know this value, let's look at what we are going to do now. Okay, so we know IA, okay, to be equal to 45 on 97 amperes. Okay, let's write this down. Okay, okay, so this is IC that we have here. Okay, so now let's look at the current moving towards this node here. Okay, let's look at the current moving towards this node. So you're going to see that the sum of the current moving towards the node equals what, the sum of current moving away from the node. So you have what, IA to be equal to what, IN plus what, IC. Okay, so you want to find IN here, so that would be IA minus what, IC equals what, In. So you can see what In equals what IA minus what IC. So you know IA to be what? You know what? IA to be what? 45 on what? 97. So that we got what? 45 on 97. Okay. Minus what? IC. Minus IC, which is what? 40 on what? 97. Okay, so this will give us let's see, 45 on 97 minus 40 on 97. So this will give us 5 on 97. Okay, that's 5 on 97 amperes. So that's what the value of what In. Okay, so now I'm going to teach you another way to calculate for the value of what In. Okay, so let's look at how you're going to do that. So we know IA already, and then we know what In equals what IA minus what IC. So all you have to do is to calculate for the value of what IC. And then in the previous approach, we found what IC1 and then IC2. But in this approach, we are going to find IC straightforward. So to find IC, we will have what the total current. Okay, you're going to use the total current and then find what IC by what applying what the current division rule. So we have what IC to be equal to what the total current, which is what 60 on 97. Okay, times this 8 ohms here. Okay, divided by what 8 plus what 4, and that's what 12. Okay, so divide by what 12. When I do this, this will give me what 40 on 97. Okay, and that's the value of what IC. Okay, so with this value of IC, you just come and substitute. You just come and what substitute into this equation that we have here. Okay, because we already know what IA, and then IA is what 45 on what 97, and then IC is what 40 on what 97. So then we get what this same value that we have here, and that gives us what 5 on what 97. So if you don't want to use the first approach, you can use what this approach. This approach seems easy, but I wanted us to understand what this all means. That's why I used the first approach also. So if you want it in a fast way, you can use what the second approach. Okay, so now that we are done finding Norton's current, we have to what find what Norton's resistance. So let's go ahead and then do this. Okay, so to calculate for Norton's resistance, this is how the circuit is going to be. Okay, so you are going to short circuit all voltage sources and then open circuit all current sources. So you see that the 10-volt source is no more here, and then you have an open circuit here because this is where what Norton's current was. So that's considered as what as a current source. So you have to what open circuit it. Then calculate for the what total resistance. Okay, which is what Norton's resistance. Okay, so what I'll do is that I'm going to transform this circuit that I have here. Okay, I'll transform it to what I have here on the right hand side. Okay, what I have here is the same as what you have here. Okay, this is because when you look at these 12 ohms here, okay, it is connected to what terminal C and then terminal what D. Okay, so instead of me using this long path here, okay, I can simply connect it in between what C and D at this side here. So that the circuit will become what simple. Okay, so that's what I did on the right hand side here. So instead of me doing this long connection here, okay, I simply connected it in between what C and D here. Okay, because what that's where what those are the nodes that what it is connected to. So I just connected the 12 ohms to what node C and then node D here. So it is the same circuit that I have here on the left that I've transformed to what I have here on the on the right. So see that you have the A here, you have the A here, you have the B here, you have what the B here. So it is what that same circuit that you have transformed. So you see that what you have here on the right side what looks much more solvable than what you have here on the on the left side. So we are going to use what this transform circuit here to calculate for the what equivalent resistance, which is what Norton's resistance. So let's go ahead. Okay, so from this circuit here, okay, you see that what you don't have any of the resistors connected in series and then any of them connected in a parallel connection. So I'm going to use the delta star transformation method here to find what the equivalent resistance, which is what Norton's resistance. Okay, so let's do this. Okay, so to do this, you are going to what change the delta network, okay, to what a star network. So let's look at how you are going to do this. Okay, so you need to what find the resistance A, B, and then C. Okay, so to find resistance A, that will be equal to what 2 times 4. Okay, you multiply these two with this 4 here, and then you divide by the total. So that will be 2 plus 4 plus 12. Okay, so that was 18. So 2 times 4 divided by what 18. So let's see the value of this. So this will be 8 over what 18. And then this can be simplified as what 4 over 9. So this will be equal to what 4 over 9 ohms. So that's the value of what A. So now let's find B. So B will be equal to 2 times 12 divided by 18. Okay, and that will be equal to 2 times 12 divided by 18. That will be equal to 4.3 ohms. And then C will be equal to 12 times 4. Okay, divided by 18. Let's see the value of this. This will be equal to 8.3 ohms. So we found the value of what? A, B, and then C. So all we have to do is to take out the delta network and then use the star network since we know the star values. So let's look at how the circuit will be. Okay, so this is the circuit that we have now. Okay, so this is the circuit that I have now. So you see that now you have some of the resistors being in series and then some to be in what parallel connection. So you can now use this transformed circuit to calculate for what Norton's resistance. So from here you see that these 4 ohms here and this 6 ohms are in series connection, and then this 8.3 and then this 8 ohms here also are in series connection. So you can add these two resistor values on what both sides. So let's look at this. So doing this, I have what 4.3 plus 6. Okay, and then that will be in parallel connection with 8.3 plus 8, and then they will all be in series. Okay, all this will be in series with the 4.9 ohms resistor. Okay, so let's look at that. So we are going to do the values in the brackets first. Okay, so 4.3 plus 6. 4.3 plus 6. That give me 22.3. So that will be equal to 7.33. And then 7.33. And this will be in parallel connection with 8.3 plus 8. That will be 32.3. And that's equivalent to 10.666. So that will be parallel 10.67. And all this will be in series with what 4 and what 9. So let's do it what's in the bracket first. So you have what 7.33 times 10.67. Okay, divided by 7.33 plus 10.67. Okay, then all this plus what 4 on 9. So that will give us the value of what Norton's resistance. So let's further simplify this. So 7.33 times 10.67 divided by 7.33 plus 10.67. That'll give me 4.345. Okay, so I'll have what 4.345 plus 4 on 9. Okay, so let's add these two values and see what we get. So 4.345 plus 4 on 9, that give me a value of what? 4.789 ohms, which is equal to what? 4.8 ohms. So you have what? Nothing's resistance to be equal to what? 4.8 ohms. Okay. So now that you know nothing's resistance, and then we know nothing's current also, you can go ahead and then draw out nothing's equivalent circuit, and then you will use this to calculate for the current flowing through the 10 ohms resistor. So let's go ahead and then do this. Okay, so now this is nothing's equivalent circuit where you have nothing's current here, you have nothing's resistance here, then you have what? The 10 ohms resistor here. So I'm going to use this circuit to calculate for the current flowing through the 10 ohms resistor. Okay, so let's look at that. So you know the total current, okay, that's the source current here. So you're going to use what? Current division rule here to find what? The current flowing through the 10 ohms resistor. So which will be what? Current I. So you have this current I here, okay. The current I, which is the current flowing through the 10 ohms resistor, to be equal to what? The total current, which is what? Nothing's current. That will be 5 on what? 97, okay, times this resistor, which is 4.8 ohms, divided by the sum of the two resistor values. So which will be what? 4.8 plus 10, that will be what? 14.8. So let's calculate for this value. So 5 on 97 times 4.8 divided by 14.8. This will give us the current flowing through the 10 ohms resistor to be equal to 0.0167 2 amperes. Okay, so this will be the current flowing through the the 10 ohms resistor. So that's the answer to this question. Thank you very much for watching this video.